One thing I noticed is that the people way in the back may not be able to read the code that I have in my slides. So if you go to my website real quick, I posted them in PDF so that if you wanted to download them and follow along. I made the font pretty big, but since there's only like these screens. Okay, so real quick, I work for Mint Digital, and like everybody else, we're hiring. So I study at Columbia University, and one of the things I'm really interested in is this topic, collective intelligence. So this is like the longest title for a talk ever. So what do I mean when I say collective intelligence? Really, this talk is about recommendation systems. And if you've read the O'Reilly book, recommendation systems occupy like 1 or 2 chapters in the book. There's a lot of other stuff in there. But for this talk, I'm just going to focus on recommendation systems, and also known as collaborative filtering. The idea that you're bringing in data from a lot of users and putting it to use to make filtering choices for everybody. So just to ground it in reality, I want to start with some examples of it in the wild. So this is one you're probably all familiar with. It's Amazon, the book recommender, which in the beginning when I first started using Amazon was pretty good. But like I bought a book on JXTA, which is like this Java P2P library. I bought that like, I don't know, 6 years ago. And now it's still recommending stuff, so not always, really good. LinkedIn has this one. If you look on the right-hand side, it says people you may know. By the way, Jacob Harris, why have you not linked with me? What the hell? Facebook, also people you may know. But beyond just products and people you may know, music, obviously, Last.fm. So there's a whole section, obviously a lot of what Last.fm does is based entirely on recommending music to you. Snooth is another example. It's still products, but in this case it's wine specifically. So I did a search on Pinot Grigio, and here on the left you can see similar wines. Yahoo Movies has something. Now, I don't really use Yahoo Movies. So when I first started, they said, rate some stuff. And the stuff they're asking me to rate, I haven't seen. So unfortunately, there is that issue of where you get your data from and how do you make a recommendation system that's legit before you have data from a specific users. And these were the recommendations it made, which not really interested in. So again, with recommendation systems, it's kind of a sliding scale. Sometimes you get good ones, sometimes you don't. But there are a ton of other examples. StumbleUpon, Google Suggest, iTunes, IMDb, Rotten Tomatoes, Yelp. There was a new one that just came on the scene last week or 2 weeks ago called The Filter, which is, again, just like a recommendation system for content and stuff like that. But the one recommendation system out in the wild that I consider the biggest and baddest example and the most successful example of a recommendation system is ads, Google Ads. They track click-throughs and stuff like that. So it's contextually based, yes, but it's also based as well on people clicking through on the ads and stuff like that. So they're recommending ads that they think you'll click on. So after all this is kind of like the sales pitch for why you should care, why would you actually want to implement a recommendation system. So this idea of serendipity, and other than being an ice cream shop north of here and a movie with John Cusack, it's also this. The faculty or phenomenon of finding valuable or agreeable things not sought for. So that, in my theory, at least I think, leads to happy users, additional sales with Amazon, obviously. If you're selling products, it becomes a pretty obvious thing. But also more page views per visit. So if you're based on an ad model, then obviously that's good. So some other ways to think of the problem of recommending stuff, you can think of it as like a ranking problem. So if you have 500 things that you could possibly recommend to the user, how do you rank them and say, these are the few things that you would want to list at top? It's a prediction problem. You're predicting whether or not a user is going to be interested in something. In the case of like movies or stuff like that, where you're giving it a star rating, you're predicting like what they would rate a movie. And it could also be just a classification problem. Would they be interested? Would they not be interested? So before I get to like some crazy like math style stuff, I just wanted to show like a really simple example. And it's a Twitter like who you should follow recommender. And at the time when I wrote this, when I was preparing the talk, there wasn't one available, but of course now there is. So not by Twitter, but by somebody else. So here's the code for it. Basically, I'm just getting the user, I'm getting their friends, and then for each of their friends, I'm getting their friends. So I'm going one level deep. And I'm just creating lists of those people, of their IDs. So my original idea when I did this was I figure I can see the friends of my friends and do a pairwise intersection. So if two of my friends are following the same person, that person may be interesting for me to follow as well. The truth is, like, you could do it simply like a count. This person is followed by 10 of your friends or whatever. So here's the basic code for it. I just go through each pair, and there I'm doing the intersection, like the common friends between the two people, and I'm just counting them up. So once I've done that, take out all the people I'm already friends with, and of course take out myself, because realistically I'm probably going to show up there in that list. So, and then just sort them based on how many they're doing. So the question is, like, how good is this? Does it actually produce legitimate results? I mean, it's really, really simple, but the thing that I found was that it's actually pretty effective. So I ran it for Trotter, and at the time I ran it, so at the top you see he's following 5 of the top 10. For me, that was kind of like, how do I evaluate whether or not the algorithm is actually making good recommendations? I figure if they're already following some of the top recommendations I'm making, then it's probably pretty good. So just going that level deep, you can see that there are 1,429 people that I could possibly recommend. So I just picked off the top 10. And as you can see from the different names, those are all people in the Ruby community that he should probably be following. So now I want to talk about like the actual stuff that's a bit more complex than something like a follow recommender. So when you're dealing with these kinds of systems, there's 2 different kinds of data you can get. There's implicit data and explicit data. So the examples of implicit data are like purchased items or viewed items, if you're doing like a feed reader stuff that they clicked on or something like that. Time spent viewing items, click-throughs, obviously. Last.fm has this thing called scrobbling, which is like a plug-in to iTunes, and it'll track what you listen to in iTunes and just report it back, so that when you go onto Last.fm, it can make recommendations of other stuff you could listen to. Explicit data is when you tell the user, we want actual information, like just give us information. So pairwise is you have 2 things, and you say, which of these do you like better? So there's a website like Command Shift 3 that kind of does that. There's the classical like star, grade, or numerical rating. So on Netflix, if you're giving it stars or whatever. There's an ordered list, which is just give you a list of items and say, rank these in the order that you like them. So number 1, 2, whatever. So there are also different types of recommendations. There are content-based recommendations. Like part of the AdSense thing is obviously content-based. I think actually another good example in this is if you look at Last.fm or Pandora, they're both music sites and they both make recommendations. Pandora's kind of a mix. Like Last.fm is just statistical, whereas Pandora is kind of content-based because they have people flagging stuff as it comes into the system. So there's user-based. These users are like these other users, so they should follow each other. And then there's item-based. If you bought this item or if you're interested in this item, these other items are like it. So the basic strategy when you're putting this together is you map the data into a Euclidean space, and I'll define that a little bit better in a second. You calculate the similarity using some sort of metric, and then you use the similarities to recommend whatever they should be following. That's the really high-level overview. So when you're doing this, you represent the data as vectors. So what that means is it's just a matrix. It's a table of data, and it maps all your data into an n-dimensional Euclidean space. So to make it, to kind of visualize the whole thing, I'm going to give like an example. So in this case, I have users in like a movies system, like a movies recommender. So I have 4 users in the system, Paul, Brian, Trotter, and Josh. And I have 2 movies that I'm comparing, Fight Club and The Matrix. And I want to find which users are like which other users. So in table form, it might look like this. So I thought Fight Club was totally awesome, and maybe I didn't like The Matrix as much. Trotter thought they were both mediocre. I don't know why, but Brian thought they were totally awesome, and Josh was somewhere in the middle. So the other thing you might notice is this looks a lot like if you were creating data points in a regular like spreadsheet, Fight Club would be your x-axis, and The Matrix would be your y-axis. So visually, that looks like this. You have The Matrix, and you have Fight Club, and you have Trotter and Josh and Brian and Paul as those specific little points on where they rank these things. So visually, you can say, oh, well, Trotter and Josh are probably similar, and they would like the same kind of stuff. And Brian and Paul are pretty similar. They might like the same kind of stuff. So if you're not like dealing with ratings, like star ratings, in this case, this is just like another example where it's people following people. So a 0, they're not following. A 1, they're following. So Trotter's following Paul and Brian. I'm following Trotter and Brian is just following himself. So here's another like movie ratings example. 4 different users, different star ratings. In this case, I've got floats as well as regular integer values. And each column is just a different movie. So as you can imagine, like that can blow up pretty quickly. And yet another like visualization of similar items. So in this case, if we're taking distance as the metric, you might figure like all the pluses down on the lower left are like each other, and all the circles are like each other. And those can represent users or movies or whatever kind of thing you're recommending. So how do you determine similarity? So there are a certain number of metrics you can use. There are plenty more than what's just listed here. Manhattan distance, Euclidean distance, cosine. Levenstein is like for strings, how close they are. The only 2 examples I give later on are Euclidean and cosine. So this is what graphically Manhattan and Euclidean looks like. Manhattan would be like the red or the blue or the yellow, and Euclidean is just the green, like the shortest distance between 2 points. Cosine similarity is just the angle between 2 points. The thing is, like, if you choose to use cosine similarity versus Euclidean, it has different effects. Because if you look at point B, if it were like higher up and to the right, it could share the exact same cosine similarity, but the Euclidean distance would be much further. So, and the thing is, like, you kind of have to play with these things to see. So one of the libraries I use is LinLG, or LinAlG, or it's a linear algebra package that was written originally in Fortran and into C, and I'm calling it from Ruby. So calculating cosine similarity is pretty easy with it. You have a movie vector and a user, and you compute the dot product of the two divided by the norms. So the other methods, like once you have a similarity metric, you can figure out, okay, how do I find other things that are close to this thing? So these are generally called like nearest neighbors methods. So the really simple one is just k nearest neighbors. So if I have 500 users, I just have one user, I pick him out and I say, who is most like this user? And I just loop through all the other users and I find, k nearest neighbors. So if I want to find the 3 most similar users. So it's easy to compute in parallel because you can compute the similarity for each point in a different process. And unfortunately, it's computationally expensive. And it can be expensive as far as the data, too, because you have to look at all of the data in your system. So some of the things you can do are there are various partitioning schemes to partition the data out into separate areas, so you only have to evaluate a subset of your data. And there's also dimensionality reduction, which I'll cover. So I wanted to use a real data example. The problem with a lot of the recommendation things online is they use really toy examples with 10 different users or 10 different items. And of course you can compute the similarity on that because it's a very small data set. So I chose to pick up the Netflix data set. So a few years ago, Netflix announced a challenge to say we want to improve our recommendation algorithm for movies. And they released a data set. And they said, if you can improve this by 10%, then we'll give you $1 million. And it's actually still open. Nobody has been able to solve this and claim the $1 million prize in a few years. But the data set consists of 17,000 different movies and about 450,000 users. Obviously, that's not all the users in their system, so they just sampled. But the sampling of users is supposed to represent the distribution across all their user base. So at first, I tried to parse it, but then I said, OK, I'm just going to actually put it into a database. So here's the basic schema. I have a users table that just has a Netflix ID, which is the map to the Netflix ID. And I add an index on that because I have to look up on that a bunch. A movies table, which just has the title, and whether or not I've imported the ratings. And then the ratings table, which just has the user ID, the movie ID, and the rating itself. And I add an index on the user ID and the movie ID because, again, I'm looking up on those a lot. So here's the movie model. So it has many ratings. I order it by user ID, and the reason I'm doing that I'll get into in a second. And I just have these two methods for storing similarities. I don't actually store them in the database anywhere. So this is the really short, this is the whole algorithm for computing the nearest neighbors. So I'm looking up the matrix as my example movie. The second line is supposed to be movies. So I grab the ratings of the movie, and then for all the movies, I just loop through, and I compare them. So you might wonder why I'm doing rating.findAll by movie instead of just doing m.ratings. Well, the problem is because the data set is so huge, it won't all fit into memory with ActiveRecord. I tried doing it just by eager loading at first, and after the top 3 or 4 rated movies each have a couple 100,000 rankings, so that ends up being an obscene amount of memory, more than my laptop can handle. So I pull them out into this compare rating so that on each iteration it'll release the memory. The GC will end up cleaning that up. And then ratings pair is the class I use to actually calculate the distance between 2 different movies. So you have 2 sets of ratings, one for the matrix, it's always going to be the matrix, and the one is for whatever other movie. And in my case, I chose to use Euclidean distance. So also the bottom line So I sort the similarities by the Euclidean distance, and I just take the top 5. So I'm doing like the 5 nearest neighbors. So before I get into the rating distance thing, I just wanted to show like the algorithm for Euclidean distance is ridiculously simple in mathematical terms. Like you have 2 vectors, and you just do that. Like you sum up you square the differences of each dimension, and take the square root of it. But here it is in code. So ratings pair, this is the initialize method. I take in the 2 sets of ratings, and I have to keep track of what movie rating I'm looking at and what comparison rating I'm looking at. The reason for that is that unlike this example, where P and Q both have the same number of actual variables, like actual dimensions, with the movie ratings, it's a sparse matrix. So not every user has rated every single movie. So I have to keep track of that. So here's the calculate distance method. So basically what I'm doing is I'm iterating over these 2 lists in parallel. And I'm just, if the user IDs match up, then I add that to the distance. Like I take the difference and square it, add that to the distance. If they don't match up, then I take the lesser one, I square it, and I add that to the distance. And I increment that counter by 1. So the 2 lists are iterating in parallel, but not always the same. Like one will be here and one will be here, and they'll like catch up to each other. So this was like my best effort to try and clean this up. Originally I had this as just like one chunk of code that was completely unreadable. So I broke it out into these different like methods. So if ratings are from the same user, increment the both. Movie ratings, and the user ID is less, which there you can see that's why I actually ordered it by user ID, is because I'm using the user ID as like the actual dimension of the vector. So those methods. Oh, and then at the end I'm not totally done. Because the truth is, like, I could have one set of ratings that are much, much larger than all the others. I need to add in all that extra distance. So I just add in the remaining distance on the remaining compare ratings and the remaining movie ratings. Obviously, one of those is going to return a 0, but that's fine. And then I just return the square root of it. So this is what those other helper methods look like. Ratings from the same user, ratings less than. When I increment both, basically finally there's the math part. So rating.rating and the compare minus the compare rating and square it, and then increment both, and vice versa for the other ones. So and remaining distance. Sorry, Ryan, it's inject. I know. It's just the rest of those, and you just square them. So here are some of the results. So I said before that the matrix was like my test one. I wanted to pick a movie that I thought everybody in the room had probably seen. We're all computer nerds, so Matrix I thought was good. So The Fifth Element, Terminator 2, Blade, The Matrix Revolutions, Total Recall, and The Matrix Reloaded. I think those are pretty good. I think those movies are appropriate matches for the regular Matrix. But again, that's one of the problems with these kinds of systems is it's not guaranteed. Like sometimes it's going to be appropriate, sometimes it's not, and it's also kind of a value judgment, whether or not you think they're good. So, but one of the, I had major problems doing this whole thing. So I didn't actually run it on all of the movies. I just looked at the top 500 movies in the sense that the 500 movies that had the most ratings, those are the ones I looked at. Because the data set is just way too huge. The movie with the most number of ratings was Miss Congeniality, and it had like 240,000 ratings, something ridiculous. And obviously the curve, looks kind of like a long tail, or maybe more like a fat tail kind of curve, or a fat middle. But so like the 500th place movie had 50,000 ratings. So all of those together represent greater than 50 million ratings still. So to keep that all in memory was obviously too big of a problem. Too much CPU work, and also just grabbing the data. So despite the fact that I had an index on movie ID, so when I looked at a movie and I was pulling back its ratings, the index is there. But the thing is, if there are 230,000 different records, those aren't necessarily all in sequence on disk. So that could actually end up being 230,000 different IOs, like different pages that you're pulling back. So obviously that was a really naive way to organize the data. But when you're dealing with real data sets that have a lot of records, you have to figure out how to deal with these kinds of problems. So with my naive method, the comparison took about 30 minutes on my laptop with just 500. So when you're dealing with that, with that much data, you have to bend space and time. So in the sense that you really have to, one of the things is like you can reduce the amount of data that you're dealing with. Some of the methods are prototype selection. Netflix did this already with their data set. They're not giving you the entire data set. They're just giving you 480,000 users worth. So prototype selection is grabbing a subset of the data that you think represents the overall larger data set. So it makes the problem tractable. It's less memory, less CPU. But sometimes, depending on how you do your prototype selection, the recommendations may not be as good, or they may not be as wide-ranging. So then, reducing the amount of work. So this is bending time. Reducing the amount of CPU work you have to do. So some of the strategies are dimensionality reduction, singular value decomposition, also known as latent semantic indexing, clustering the data so that you can figure out what cluster an item belongs to and just look within that area. Locality sensitive hashing, which is basically just like you have a set of hash buckets and you toss all the data points into different buckets, and when a new point comes in and you want to figure out what's like it, you just hash it into a bucket and you look inside the bucket that it's in. KD trees, which is just another way for sorting out the data so that you only have to look at a subset of it. So the general reduction strategy is you calculate the clusters, or you do the dimensionality reduction, or you assemble the KD tree. And then for each item, you find where it belongs, and you only calculate similarity within that area. So one of the clustering things you can do is k-means. So in this graphical example, you start off and you say, OK, I want 3 clusters. So you see the red, the green, and the blue points. Those are called your centroids. And it just iterates over this, like moving them gradually, so that eventually you end up down on the bottom right pane. So you have your centroids placed, and you have your points that are closest to each centroid. So when a new point comes in, you compare it just to the 3 centroid points, find which one it belongs with. Once you've done that, then you just look at the points that also belong to that cluster. So hierarchical clustering is another thing you can do, and you can actually work up the hierarchy to make it more broad or include more data points. So an SVD example in Ruby, obviously you probably don't want to do actual linear algebra in Ruby because it would be slow and not good. So the 2 different things I found were the linalg gem, which I said uses LPACK, and Ruby GSL. I went with linalg. It is a royal pain to install, but I did get it running. So because the reason why it's kind of a pain to install is you have to have a Fortran compiler to compile the Fortran version, and then you need the Fortran to C compiler to make it into C, and then you can hook it up. So here's an SVD example for an item-based approach. So again, I'm looking at the movies data set, and I'm trying to figure out what movies are like what other movies. So one of the things that becomes kind of a pain in the ass when you're dealing with this is tracking how you've set up your matrix, your vectors. So which rows map to which IDs. In my case, I've got users as the rows and movies as the columns. So which rows, user ID rows, match up to which IDs. And then same thing with the movies, like which IDs map up to which column. So because, like, again, if movies are columns, column 1 may be the matrix, column 2 is Fight Club, and column 3, all the way up. So if you're working with the entire Netflix data set, you'd be dealing with a matrix that's, that has 450,000 rows and 17,000 columns. So it's a pretty big matrix. So, you know, just a couple of methods to kind of track that, to keep track of that kind of stuff. When I did the SVD one, I was actually parsing the files directly, so I wasn't actually putting it into a database and pulling it out. And the way this particular data set is lined up is that it's one file per movie that they have, and they just have all the ratings with the user associated. And it's just too much. It's too many users, too many movies, too many ratings. So I took a subset of it, again, but this time I only used 100. So this is kind of like what it would look like, you know, as a Ruby matrix. So linealogy, if you're doing, like, if your movie matrix looks like this, which obviously I assembled based on this isn't the actual one. I assembled it based on the parse data. But you spit it at linealogy. You compute the SVD decomposition. If you don't know, like, what SVD is or how to actually do it, it doesn't really matter. You can kind of treat it like a black box. So you just, what it gives you back are these 3 different matrices. So I decided to take a rank 4 approximation, which is I'm reducing the dimensionality of the matrix down to 4 dimensions. So it'd be like 4 columns. So then another housekeeping method, like for a specific movie, give me the column vector for it. So all the users that rated the movie. And the thing is, I actually have to assemble it in the right way so that the users who didn't rate it are actually, you know, zeros, and the users who did show up in the right spot. So in this particular case, I actually used cosine similarity, which again, like with linealogy, is pretty easy to compute. But in the end, you kind of get this number of, okay, here's the similarity between the two. So the results that I got out of this, and the movie I actually did for this was The Matrix Reloaded, again, because I figured everybody's probably seen it. So, but here were the recommendations. Apparently, anybody by this measure, anybody who likes The Matrix Reloaded would love the entire Lord of the Rings franchise, and Swordfish, because that is the best hacker movie ever.
I don't know if it's because of that.
Oh, it's so good.
I think those are people who have a high threshold for sequels.
That's true. That could be. So this ranking was actually just based on the cosine similarity. So those are the direct similarities that it output. So another strategy I thought of is, okay, I'll change this up a little bit. So I'll predict the similarity, but I'll just use it to weight the ranking. So basically, it'll predict what the actual, what the ranking would be for a similar movie. So here's the code for that. I go through the different similar movies. I just do the weight, and there's inject again, sorry. And I just do like a weighted average of all the things, and I normalize it. So here are the weighted predictions that I got out. Lord of the Rings is still up there, but the first Matrix made it in, and Swordfish got bumped out, which I think is actually probably appropriate. So some of the things that you can do, like you want to calculate this stuff offline, even for something as simple as like a follow recommender for like LinkedIn or Facebook or Twitter. that's probably not something you want to calculate every single time a user hits that page. I mean, you could do caching with that, but then you have to deal with like warming the cache if you don't want an actual like request from a user to spawn that process of calculating. So it's actually good to do them offline through a background process. Because they're memory intensive and they're CPU intensive, you don't want to run them on your actual web server. You'd want a separate server to run them. And the other thing is like they're very, very data intensive, so you probably don't even want to run it against your actual database. You just want like a slave database that's replicating everything so that you can just pull off of that. So you can hammer it as hard as you want, and you won't have a problem with dragging your whole system down. So some future work and possible solutions. I mean, the thing is that over the course of working with this data set and looking at it, I came up with a lot of problems. Problems related to how much memory I'm using, how long it's taking, how quick something parses, and obviously just pulling back the data at all. Because if you look at like the way I pulled back the data, I say it took 30 minutes to run one comparison, like a comparison for one movie against 500 other movies. Granted, they were the top movies, and I was pulling back like 50 million ratings, but in that case, it wasn't memory or processor that was killing me. It was the actual data. It was the act of pulling back the data out of the database. So one of the things I'm not sure, actually, if ActiveRecord will do this or if it's just underlying in the database system, but if you index on multiple columns, a lot of times the database will do an index-only read. So you'll be able to pull that all in sequential I/O instead of like hammering the regular table to pull it all back. The other idea I thought is, okay, maybe you could actually have, like for each movie, just have like a binary blob field, and when you pull it back, just pull back the whole thing and read it in. I haven't actually had the time to try these things, so it's kind of, it's kind of up for debate. And then the other thing is maybe a document database would be more appropriate, something like Couch or Through or something like that. But then again, the problem is like if you're storing it in a document database and you're storing actual strings and you're parsing that out every time, parsing out 200,000 ratings or even 50,000 ratings is going to take forever. So one of the other problems I had is there's not much in Ruby for doing these kinds of things. There are a few libraries for doing classification and stuff like that, but there's not much for doing, there's nothing for doing clustering and stuff like that. Now, if you're just doing the naive version of k-nearest neighbors, you can write that really in like, 5 lines of code. So one of the things I'm working on is the Bassett gem. I'm building it specifically to be like a generic abstraction for doing machine learning kinds of tasks. So a lot of gems out there, like there's a cluster gem, but it's focused only on text. So I'm trying to build it to be like generic so they'll work for any sort of like machine learning task that you'd want to work with. Right now it's only for classification and feature selection. But I do plan on actually putting clustering code in there. And one of the things I was also thinking about as I was doing this is I was thinking maybe JRuby might be a solution to this, because there are obviously a lot more libraries available. The Weka library, which is a really good library for doing machine learning tasks, is available. And if you do have to tune, you would be able to drop down to like Java data types and use smaller data types. I mean, obviously in Ruby you can always drop down into C and use smaller data types, but it seems at some point yes?
Did you measure just not using ActiveRecord?
I had a memory problem before I even used the ActiveRecord. Like ActiveRecord adds maybe 20 meg onto the footprint of the running process, and then obviously AR objects themselves use up a little bit, so you've got...
It's not a little bit at that scale. When you've got that many, it's a lot.
No, right. Obviously, like it scales up. You have an ID per thing, but I mean...
No, it's just like there's all the built-in methods. Like as somebody who's actually written like a light version of ActiveRecord to get like lots of things at once?
Right, but each one of the methods for each object doesn't take memory, does it?
Doesn't really matter, Francis. Like any data set that you would want to do this on would be too large.
Right, you're probably right.
Actually
It's
do
the
it.
scale, yeah.
And
So-
even if you were writing raw C to hook up with MySQL or whatever, it'd still be too big.
Right. So really, I mean, that's the issue is like if you have a small enough data set, it's totally feasible to use ActiveRecord and deal with it. And maybe that's how you want to start off. You know, don't optimize prematurely and just go with whatever's simplest and what works. And so again, like with this kind of stuff, there's a lot of open problems still. Obviously, if Netflix is offered $1 million and still nobody is like stepped up to the plate and like claimed it, there's still a lot of things that they're trying to figure out with these kinds of systems. So that's the end of it. Thanks, everybody.
Let's start with Mike and Jim.
I've actually used Quacker with JRuby as well.
It's good?
Yeah.
Nice. Brian?
Yeah. First off, I just want to say,
Microphone coming to you.
He's going to correct me on the ratings.
Okay. So first off, I want to say that during the second half of your talk, I implemented your friend recommendation engine for WePlay and got that running. So that was pretty cool. But what I wanted to ask was, how do you test, and it's really easy to do for anyone who's looking, but how do you test like a friend recommendation engine well to know that you know it's actually recommending friends correctly?
So, I mean, that was one of the problems is you can test to see if it's, obviously, if it's working at all. And that was one of the things I said is a metric I chose was if the people who were recommended, like if they were already following a certain number, so like WePlay, if you're recommending the top 10 friends, don't filter out the ones they're already following at first. Or if you do, find out how many of like the top friends that you filtered out they're already following. I mean, it stands to reason that if they're following 10 of the top 10 people and you just go further down the list, it's probably working pretty well. But again, like testing these systems, with the Netflix system, what they have is they have the user data and they have like the training set, which is a bunch of rankings from a bunch of users on the movies, and then they have a holdout like test set. So you train your recommendation system on the training set, and then the test set is just users, movies, and movies that that aren't in the training set or aren't ranked in the training set by that particular user, and the ranking. So what you do is you predict, okay, for this particular movie, the user's going to rate it 3 stars. And you just go through the whole test set, and you say, how many predictions did I get right? And when you're doing that, like there are these different things, like you can optimize for different loss functions. So if you got a ranking wrong, what is the penalty your algorithm pays? So one of the very really simple one is like squared loss. So if you predicted that they would rank it a 5, but they actually rated it a 3, your squared loss is 4. Difference squared. So with the Netflix one, they give you they tell you how their recommender is doing on this data set, and you just have to see if you can improve that by 10%. So that's one of the things you can do is hold out a data set and use that to predict. And one of the other things you can do is you don't have to hold out one specific set. You can do something called cross-validation. So the really simple cross-validation thing is 10-fold cross-validation. You take the data, you split it up into 10 different chunks, you train on 90% of it, you test on the remaining 10%, and you calculate how well you did, and then you just iterate 10 times. And then you output that. So that's one of the things you can do. Is there anything else? Yeah.
Get a mic. Sorry.
What about existing libraries like libsvm? Have you heard of that?
Yeah.
That it seems like offloading, basically, giving all your data to some big engine that's already written in C and optimized would be the way to go.
Right. So initially I thought, I'll use linLG and I'll avoid that. But the problem is eventually I have to have all the data in memory as Ruby objects before I feed it to linLG. So yeah, the actual computation runs really fast because it's in C, but it doesn't help me on the memory side. I'm not sure with libsvm if you can do that. I know one of the things you can do is you can just output like a file, and you can represent all your data as like the sparse matrix, and then just run it as an external thing. Yeah, I mean, libsvm is for support vector machines, and I'm sure it's it's pretty good and pretty fast. There Ruby bindings do exist for it, but I think they're pretty raw. Like it looks like a Ruby library in C style. So.
Also, I would add to that if you're not an expert in this field, you should definitely stay away from support vector machines.
Yeah, they're really complex.
Because it's extremely difficult to figure out why a support vector machine told you what it told you. So you could definitely spend a long time trying to figure that out for that tiny little last bit. It tends to be you get your biggest boost with the simplest techniques.
Right. So like if you're doing classification, one of the easiest and most forgiving algorithms is naive Bayes. And that's pretty, it doesn't give you as good of accuracy as support vector machines if you know what you're doing with them. But the problem is if you, support vector machines are pretty finicky, and if you mess it up, you get horrible results. So, yeah. All right. Oh.
So I added you on LinkedIn, and are most of these algorithms actually very good to parallelize? And have you considered using something like MapReduce, maybe Hadoop?
Right. So the thing is, some of them I've definitely considered that. Some of them aren't. Like some of them are really, really hard to do. Like SVD is not very easy to parallelize, and that's one of the like secret sauces. What? No. But k-means you can parallelize. Parallel.
Yeah.
You can run it in parallel. Like that lends itself. And there are different clustering algorithms that you can run in parallel. Toby knows a bit about Hadoop and actually doing that. So.
I said stop because they're in the process of implementing SVD and probabilistically cementing indexing for Mao right now.
So it's approximation. It's not. It's not exactly. Yeah, that's like one of the secret sauces for Google is their SVD implementation that they run on those huge matrices. So do you know if they've done that yet?
Yeah.
In Hadoop, it's already ready.
Oh no, not in Hadoop, but
okay.
Google has it.
Yeah.
It's doable. Yeah.
It's doable for sure. Hard. Okay. All right, I think that's it. Thanks.